isomerism right now. In that one, so what is meant by the optical isomerism and what is meant by the chiral, what is meant by the achiral, okay, and how to calculate the total number of stereoisomers and how to calculate the total number of optical isomers also isomers and how to calculate the meso isomers also we had seen in the last class. Is it clear? So I give some formulas also to calculate the optical isomers, total number of stereoisomers. Okay, so based on the number of chiral centers, we can calculate the total number of stereoisomers. Okay, if it is the terminals are not same, if the terminals are not same, means what is the formula we are using to calculate the total number of stereoisomers?
Sir, 2 power n minus 1.
Total number of the terminals are not same. The terminals are not same. The terminals are not same means what is the formula we are using means here 2 power n only. Okay. So 2 power n is the formula we used. And if the terminals are same and condition applied, first condition, the given compound is having even number of chiral centers means what is the formula we are using means 2 power n minus 1 plus 2 power n by 2 minus 1. Okay. In that one, 2 power n minus 1 is represented as a number of optical isomers and 2 power n by 2 minus 1 it represents as here number of meso isomers. If you add total with then only you will get as a so total number of stereo isomers. Okay, and one more formula also is we used. If it is having odd number of the chiral centers, if it is having odd number of chiral centers means what is the formula we used? Odd number of the chiral centers. Odd number of chiral centers means formula is 2 power n minus 1 plus 2 power n minus 1 by 2 the formula we used. Okay, already I forwarded notes also in PDF formation. Okay, so once you go through the notes also after finishing of your class, otherwise when you will be free. So as per your request only, every class I am converting to the PDF and forward I am updating that one in resource file here. Okay, so from there you can check it out what are the formulas we use and what are the examples we had seen also. Is that clear? Okay, next one. And so today also we are going to discuss about the optical isomers JEE level we are discussing. Okay, so here biphenyls and allenes also they exhibit as an optical isomerism. Okay, so which one are they exhibit as optical isomerism? So biphenyls. So which we can call as a biphenyls. What is meant the biphenyl? So JEE level concept. So biphenyls and allenes also they exhibit as a optical isomerism. Exhibits optical isomerism. Okay. So which one are biphenyls and allenes are exhibits. Allenes are exhibits optical isomerism. Exhibits optical isomerism. So which we can call as a biphenyls. First we can check it out the biphenyls. Biphenyls. So which we can call as a biphenyls. So two phenyl rings. That means two benzene rings are two benzene rings. So this is the one benzene ring and this is one benzene ring. If two benzene rings are connected with one sigma bond, mean that we can call as a biphenyls. Okay, so two benzene rings are connected with one sigma bond, mean that we can call as a biphenyls. So when they exhibit as a optical isomerism means in a biphenyls at ortho position, two different atoms it has to be there. Here A and here B, and here also A and here also B. So then only it exhibit as a optical isomerism. All of you, while seeing the structure, everyone will get as a doubt. Is it right? Sir, if you cut from the center, you are getting as a two equal halves. But whenever you will get as a center of symmetry means the molecule does not exhibit as a optical isomerism, but you're telling that biphenyls are they exhibit as a optical isomerism. How it is possible? That is only your doubt now. All of you, Aditi, is it right? Okay. Now, but biphenyls, the structural arrangement it will be different, ma, biphenyls. Sir, how they will be there means here, for example, actually, ma, so are you able to see? I don't know, are you able to see or not? Are you able to see me here video? Ma, here, so this is the one benzene ring. I'm adding as a one benzene ring like this. Okay, so two are present in one plane. So when two benzene rings are present in one plane, that time it becomes as a optically inactive. But in this one it will be present in another plane. One benzene ring is present in another plane. Okay, so that means two benzene rings are, one benzene ring is perpendicular to another one. One benzene ring is here exactly perpendicular to another one. So when the one benzene ring is exactly perpendicular to another one means if you divide means you won't get as a two equal halves. You won't get as here two equal halves. If you won't get as a two equal halves means then it becomes as optically active only now. Okay, so due to that reason only biphenyls are they exhibit as a optical isomerism. Okay, and some compounds are there. So this one is it exhibit as optical isomerism. So this exhibit as here optical isomerism. And one more it is there. So one more, what is another example means if the benzene ring is attaches with the two identical atoms at ortho position. JEE level question, this one is. Okay. Here also it ortho position A and B it is there. If this benzene ring is attaches with the two identical ones, A and A and A means it does not exhibit as an optical isomerism. Sir, why it does not exhibit as an optical isomerism means it has a plane of symmetry. Okay, it has here plane of symmetry. Okay, so plane of symmetry it is there. So while having the plane of symmetry, it is optically inactive. Whenever it is attaches with the identical atoms at ortho position, identical atoms are there means then they does not exhibit as optical isomerism. When it exhibits as optical isomerism means here ortho position, two different atoms it has to be there. Then only it exhibits as optical isomerism. Okay, so can I give one question based on this one? I'll give one example. Now let us see which of the following molecules exhibit as optical isomerism and which of the following molecule is not exhibit as a optical isomerism. Now my question is which of the following is exhibits optical isomerism. Optical isomerism. Okay, first option. Option A. Option B. Option C. Option D. So what is the correct answer? Which of the following is exhibit as an optical isomerism? What is the correct answer? All are biphenyls or not, ma? Samhita, Aditi, Anjan, Sai Akshit. Which one is exhibit as a optical isomerism? That is my question. Condition is if the biphenyl which is attaches with the two different groups are present at ortho position, then only it exhibit as optical isomerism.
So is it C?
Very good, Aditi. C is the correct answer. Okay, so what is the correct answer means here? C is the correct answer because of condition applied. So what is the condition means? Biphenyls at ortho position two different atoms it has to be there. Only ortho position only we are considering. We are not considering any meta position. According to that one, first we can check it out here in the first structure. So in the first phenyl group is two iodine and bromine are attached with the ortho position only. But in the second structure, iodine is attached to the meta position, so it is not possible. And in this one also, if you see, iodine is attached at meta position. And the third one, you can check it out. So third one, biphenyls, that means benzene ring is attached with the two different atoms at ortho position are there. Okay, so that's why C only takes exhibit. So sir, you may get doubt. Sir, D also either it exhibit as a optical isomerism or not means here. D does not exhibit as a optical isomerism. Why it is does not exhibit as a optical isomerism is of course two bromine atoms are there. What I told condition has to be two different atoms. But this benzene ring is attached with the identical. If it is identical means it has a plane of symmetry. While having the plane of symmetry, it becomes as a optically inactive. Now you got the clarity, all of you? All of you got it or not? Sir, by seeing the structure, actually it is the three-dimensional structure. So three-dimensional structures cannot be represented on the plane of the paper. So that's why they look like as the same only. But the thing is, one benzene ring is present in one plane means another benzene ring is present in a different plane. So one benzene ring, two benzene rings are perpendicular to each other. Okay, if you cut any direction, you won't get as a two equal halves. That's why they are called as a they are optically active compounds. Optically active compounds are the exhibit as optical isomerism. Is that clear? And I'll give one more example, sir, here. And allenes. Allenes also they exhibit as a optical isomerism. So which one are they exhibit as optical isomerism? Allenes also they exhibit as a optical isomerism. So which we can call as a allenes. Okay. So carbon double bonds. C double bond C. C double bond C. Okay, if the double bonds are present like this means here, this we can call as a allenes. Okay, sir, by seeing the double bonds, you may get doubt. Sir, all double bonds are that means all are present in one plane means they won't be present in one plane. So that is also present in a different plane. One is perpendicular to another one, like biphenyls only. And that is also if the terminal carbon atoms are attached to different atoms or group of atoms, then only it exhibits as a optical isomerism. If it is attached with the identical one means it does not exhibit as a optical isomerism. So that means if C double bond C double bond C. If the terminal one is attached with the EAA, at this side B and B it is that means it does not exhibit as optical isomerism. Okay, so terminal carbon it has to be attached with the two different atoms or group of atoms. Then only it exhibit as a optical isomerism. Okay, so I'll give one example for this one. C double bond C double bond C. Here I and Br it is there. Here also I, here also Br it is there. And if we C double bond C double bond C, here CH3 bond H, here H bond C2H5. Right, ma. So both the compounds are they exhibit as optical isomerism or not? I give two examples here. Is the two examples are exhibit as optical isomerism or not?
No, sir.
They won't exhibit as optical isomerism. Samhita,
Same side, sir.
huh?
Not on the same side, sir. It should be on the same carbon to exhibit optical isomerism.
Of course, they may be present at same side. How we are telling that they're same side?
So they're not same side, sir.
Yes, they're not the same side. One is perpendicular to another one. So one is perpendicular to another one means here. Okay, so they will be in different plane. Two double bonds are present in a different plane. If two double bonds are present in a different plane, means they exhibit as a optical isomerism. This one also it exhibit as optical isomerism. This one also it exhibit as optical isomerism. And third one is exhibit as optical isomerism or it does not exhibit as optical isomerism. Third one, Anjan, Samhita, Aditi, Sai Akshit, any one of you. All these are the JEE type of questions, ma.
No, sir.
No, sir.
No, ma. So why it does not exhibit as a optical isomerism means the terminal carbon is attaches with the identical atoms. So whenever it is attaches with the identical atoms means it does not exhibit as a optical isomerism. Okay, so terminal has to be different, then only they exhibit as a optical isomerism. So all these are okay. So let's see which compounds are the exhibit as optical isomerism means here. The compounds which contains chiral carbon that it exhibit as optical isomerism, and biphenyls also they exhibit as optical isomerism. Okay, and allenes also they exhibit as a optical isomerism. So until here clear? Okay, so next, what is another important point? It is there in this one only. Okay, so in this chapter only we are going to study about enantiomers and diastereomers. Okay, so how many members were having clarity about the enantiomers and diastereomers? I don't know. Okay, actually optical isomerism we are going to study under the 12th haloalkanes, haloarenes chapter we are going to study. Okay, especially main important questions they are asking based on the SN1 reaction, SN2 reactions we are going to study about the optical isomerism. Okay, so they are asking the questions. What is the stereochemistry of the SN1? Okay, so what is the stereochemistry of the SN2 reaction? Okay, and some other terms also we are studying under the optical isomerism. What are the terms we are going to study under the optical isomerism means? One is enantiomers. What is meant by the enantiomers? What is meant by enantiomers? Any one of you? 12th standard students also is there now? Anjan is 12th now? Anjan, Samhita. Anna. So nowadays Sriveda is not joining. I don't know what happened to her. Now, what is meant by the enantiomers? Any one of you? Aditi, you don't know about the enantiomers. Anjan, what is meant by the enantiomers?
Sir, I don't know.
You don't know. Okay. Samhita, do you have any idea about the enantiomers?
No, sir. No idea.
No idea. Okay. Amma, so first I'm taking as a tartaric acid. What is the name of this one means here? Tartaric acid. Okay. So this is here tartaric acid. This is the tartaric acid. And mirror image of the tartaric acid, ma. Mirror image of tartaric acid. Okay, so mirror image of the tartaric acid, it becomes as like this here. OH, H, and this one H, OH, and CO, OH. Okay, so let's give this we can call as a structure 1. This we can take as a structure 2. Okay, and I'm writing as a mesotartaric acid. What is the mesotartaric acid? We got last time I wrote the structure also. I told mesotartaric acid is optically inactive, but due to the presence of the chiral center, it acts as an optically active compound. Sir, which we can call means identical atoms are present at same site means that we can call as a mesotartaric acid. Mesotartaric acid. So the mirror image of the mesotartaric acid. So we can write as a mirror image is okay. COOH and this one. Here OH it is that side. H. Here also OH and H. Exactly whatever is the mark. So this side it is there. That we are writing in opposite direction here. Okay. H COOH. So this is structure 3 and structure 4. Okay. Sir, all of you are getting my video first of all. Everyone, you are getting my video or not?
Yes, sir.
Okay, right, sir. Sir, so this is my left hand here, and I'm taking as a right hand. Okay, so once all of you check your hands also. Okay, so one hand is mirror image to another one. One hand is mirror image to another one. Okay, I'm requesting you all just close like this. So how we can keep the namaskar? Okay, so we can keep like this. So if you keep like this, you can turn this side and you can turn this side and you can check it out. Position of the fingers is same or not, ma? If positions of the fingers, your fingers, if you keep like your hands, both hands. Okay, if you keep like this means position of the fingers is same or different, Anja, Samhita and Aditi. Aditi, position of the fingers is same.
Yes, sir.
Right, ma'am. So whenever you keep like this, if the position of the fingers it is same means these two are we can consider as a diastereomers. Okay, so that means how we can keep here. So when placed, one hand is placed another one. Okay, so one hand is placed upon the another one. If the position of the fingers is same, that means if the one molecule is placed in the another one, if the positions are same means that we can call as a diastereomers. Okay, so what we can call ma? So we can call as a diastereomers. Diastereomers. Sir, what is meant by the diastereomers means here? Superimposable mirror images. Superimposable mirror images. Mirror images are called diastereomers. Are called diastereomers. Okay, so diastereomers are having same chemical properties. Diastereomers are having same chemical properties. But differ in their physical property. But differ in their physical properties. Sir, what are the examples of the physical properties? Is any example for the physical properties? Boiling points, melting points, okay, and refractive index. Okay, so refractive index, okay. So all these are the examples of, okay, so the physical properties. They have a different physical properties, but they're having the similar chemical properties. Okay, so now you got the clarity what is the diastereomers. Now, so based on this one, let's see, I give 4 structures. I give here 4 structures to you. In this one, which of the following structures are they act as a diastereomers? Okay, if half of the structure also it is going to be match means, if half of the structure also it has a superimposable means, that is also we can consider it as a diastereomers. Now my question is, what are the examples of the diastereomers in a given 4 structures? Any one of you? Any one of you, sir? Anjar? What are the examples of the diastereomers? Samhita? What are the examples of the diastereomers? Can I explain, ma? Now let's see, ma. Ma, 1 and 3 are the diastereomers. Structure 1 and structure 3 are the diastereomers. Sir, how we are telling that structure 1 and structure 3 are the diastereomers means here? Let's see, ma. So this is the structure 1 and this is the structure 3. Okay, in this one, first half part. Okay, first half part you can observe now. Here also COOH, here also COOH is there. H and OH. In this one also we are having H and OH. Okay, so that means half of the structure is, okay, so when you take this one and whenever you're placing one upon another one means here hydrogen side hydrogen is there, OH side OH is there. So that means half of the part is similar to the first structure. Okay, superimposable if one position of the hydrogen and OHs are same means that we can call as a superimposable. So half of the structure is superimposable. So due to that reason only 1 and 3 are we can call as a diastereomers. Similarly, is any other structure is going to be matches?
2 and 4.
Very good, Ajay. 2 and 4 also it is an example of here diastereomers. Okay, so 2 and 4 also it is examples of here diastereomers. Sir, in 2 and 4, which part is similar means here? Sir, in second part, okay, let us see. So which one is the similar? Sir, first above the part. Okay, above part is similar to the fourth one also. OH and HCOOH. So half of the part is having the similar. Half of the part is similar means that we can call as a diastereomers. So what are the examples of the diastereomeric pairs means 1 and 3 and 2 and 4 also we can call as here diastereomeric pairs. Okay, so now you got the clarity. And is any other structures are there? So 1 and 3 is not. 1 and 4 is 1 and 4 also. It is the example of diastereomer only, na? Anja, Aditi, once you checked out 1 and 4, because of bottom part is same. OH, H, COOH it is there. So here also OH, H and COOH. So 1 and 4 also we can consider it as a diastereomeric pair. And similarly 1 and 3 also we can take now bottom part. So this part you can check it out now. This part is similar na H, OH. For this one also here also it is having H, OH and COOH, COH. So bottom part is same. So that's why 2 and 3 also we can consider it as a diastereomeric pairs. So total how many diastereomeric pairs are there from the above 4 structure means 4 are there. How many are there? 4 are there. Okay, next. Enantiomers. Enantiomers. What is meant by the enantiomers means non-superimposable mirror images are called as enantiomers. Enantiomers. What is meant by the enantiomers here? Enantiomers are nothing but here non-superimposable mirror images are called as enantiomers. I think so already I give the heading. Is it right? Right now. So here only I give the heading here. So what is mean by the enantiomers? Enantiomers is nothing but non-superimposable mirror images. Non-superimposable mirror images. Non-superimposable mirror images are called as enantiomer. Sir, how we can identify the enantiomers means if this structure is the second structure, if directly if you lift that one, if you lift like this, and this is the one structure. Is that clear? So you observe the video once you check out the video here. Okay, so this is the one here, and this is the another one. This two structure. If I am keeping one is placed upon the another one. If I place like this means, I think so you are observing some difference. What's the difference you are observing in this one? Position of the thumbs is same or different? You can keep your hands also, opposite direction. So first time you keep like this now, however you are keeping as namaskara and all. Okay, so you can keep in the reverse manner. If you keep in the reverse manner, means this position of the fingers is same or different? Aditi, Anjan, Samhita, Sai Akshit.
Position of the finger, sir.
Position of the fingers, you can keep like this, separately one upon one.
The thumbs are different, sir.
Very good. And if you see other fingers also different. Position of the fingers you are getting as a different here. Okay, so whenever you are keeping like this means you will get as a position is different means that means non-superimposable only na. Okay, superimposable means positions are same. Non-superimposable means here they are having a difference. Okay, so non-superimposable mirror images are called as enantiomers. Okay, so enantiomers are having similar physical properties and similar chemical properties, but they differ only in rotation. Okay, here I write my here. They have similar physical properties, similar physical and chemical properties. Physical and chemical properties. Okay, but differ in rotation. But differ in rotation. Okay, so now you got the statement and if you got the some characteristic properties of the enantiomers. In this one, my question is, so which we can call as a enantiomers? Okay, I gave four structures. Which are the enantiomeric pairs? Which are enantiomeric pairs? Again, same options I am giving one. Same options I am giving. Okay.
1 and 2.
1 and 2 is the enantiomeric pair. Very good, Anjan. 1 and 2. Next.
Even I think 3 and 4.
3 and 4 also, sir. Very good, Anjan. Okay, so 1 and 2 and 3 and 4 are enantiomeric pairs. Okay, so now you got the clarity, all of you. Still anyone you having doubt until here? So which we can call as an enantiomers, which we can call as a diastereomers. Sometimes based on this one also they're asking the questions in the NEET. So JEE level examination one. They'll use some structures. You have to find out which are the enantiomeric pair, which are diastereomeric pairs. Samhita, if you're having any doubt. Aditi?
No, sir.
Aditi, do you have any doubt in this one?
No, sir.
Okay, so now until here you got the clarity now. Okay, and along with that one we have some other second one. So what is it means? Racemic mixture. Racemic mixture. Some all basic, some 12 standard basic terms here. Okay, so racemic mixture. What is meant by the racemic mixture? Racemic mixture. So what is meant by the racemic mixture means here? It is the equimolar mixture of, it is equimolar mixture of D and L isomers is called as a racemic mixture. It is the equimolar mixture of, it is equimolar mixture of small d and small l isomers. Okay, small d and small isomers is called as a racemic mixture. If it is the racemic mixture, okay, then what about the net optical activity of the racemic mixture? Net optical activity of the racemic mixture. Net optical activity of racemic mixture. Racemic mixture. Sir, what about the net optical activity of the racemic mixture? It is high, low, zero, none of the above. Net optical activity of the racemic mixture is equal to greater the value, lower the value, 0 and none of them. What is the correct answer? In definition only it is there. So racemic mixture is nothing but equimolar mixture of D and L isomers, and equimolar mixture of the enantiomers also we can call as a racemic mixture. That means the mixture is containing 50% of the D isomers and 50% of the L isomers. What is the charge of the D isomer? D isomers can be represented with the positive, na? L isomers can be represented with the negative. 50% negative, 50% positive means net optical momentum it becomes as a 0 only, na? 50 plus 50 minus, na? What is the overall value? What is the value you will get? So you will get as a 0. Okay, so hence the net optical activity of the racemic mixture is equal to 0. So why the net optical activity of the racemic mixture is equal to 0 means because of it contains 50% of the D and 50% of the L isomer. Okay, so now you got the clarity until here, all of you? Everyone. So then we'll continue in the next class, sir. Until here, just go through your notes. Okay, and based on this one, you have some questions in your modules or assignments which are you having here. So please practice the questions also. We'll continue in the next class.